So let's go over a very quick review of what we discussed last time, and what we talked about last time was, of course, the bits, or 1 byte, which is made up of bits. And we talked about that a bit is short for a binary digit. So in order for us to even talk about what a bit and a byte are, we need to know what binary digits are. So we need to know what a binary number is. So a binary number is a base 2 system, meaning you only have 2 digits, the digit 0 or the digit 1. You cannot have any numbers that are higher than 0 or 1, meaning you cannot have 2, 3, 4, 5, 6, 7, 8, or 9 appear in a binary number. This is because computers can only compute using zeros and ones. Computers don't know what the number 3 is. They can use the digits 1 and 0 to figure out 3, but that doesn't mean that they could look at the number 3 and understand what it is. So we talked about how the binary system works, and the system works kind of like switches. So you start off with 0, and as you keep progressing and adding 1, what we want to do is, if you could add one to the number, so specifically if you add 1 to 0, 0 plus 1 is 1, so that's perfectly fine. The issue was when you tried to add 1 to an already existing 1. So for example, when we had this situation, when you add 1 to 1, you normally get 2. 1 plus 1 is 2, but unfortunately the digit 2 does not exist in the binary system. That's because there's only the 2 digits 0 and 1. So what we did is reset that place value and incremented the next place value like you would in a decimal system. When you reach the number 19 in the decimal system, the base 10 system, you add 1 to it. When you add 1 plus 9, however, it is, you would get 10, which is a 2-digit number. That's because 9 is the largest possible single-digit number that you can achieve in the decimal system. So we would set it to 2 and increment the place value over 1 plus 1. Or sorry, set it equal to 0, and then we increment the next place value over 1 plus 1, which would be 2. So you get 20. Same thing for binary system. When we get here now, you can add 1 to the ones digit, the very right-hand digit. That's perfectly fine. So we just add 1 to it, and then we get this number here. But when we try to add 1 to this number, we get 1 plus 1 on the very right-hand side. 1 plus 1 would normally be 2, but there's no such thing as 2. That's because you maxed out all the possible digits that you could use. So we reset the right-hand digit and increment 1 to the next digit over, which is also a 1. But when you add 1 to that, you once again reach that situation where you've maxed out that digit. So what you're going to do is reset it and increment the next one over. So you have 1, 0, 0 as your binary representation for the value 4. And then you would continue this process. We also talked about how painful of a process this is in order to convert a decimal number into a binary number. We were doing this process of like continuously adding 1. And I presented a situation, what if you are actually trying to get to the number like 65? Do you really want to do this 65 times? And resoundingly, of course, you guys also know. So we introduced a second method, which is this one right here, using the place values. And in this case, we're specifically talking about a binary number, a base 2 system. We were going to use the powers of 2. Because in a decimal system, if we analyze the place values, these are all done in the powers of 10, starting from the very right-hand digit. The right-hand digit over here, the ones place is it's the ones place. The next digit over is in the tens place, then the hundreds place, and the thousands place, and the 10,000s place. And writing these out into powers, we see that they are powers of 10. The ones place is 10 to the 0 power. The tens place is 10 to the first power. The hundreds place is 10 to the second power. Thousands place is 10 to the third power. And the last place value that is available to us in this number is 10,000, which is 10 to the fourth power. So if we convert this not into a base 10 system, a decimal, if we use it for the binary system, which is base 2, we, instead of having like 10 to the 0, 10 to the first, 10 to the second power, we get 2 to the 0, 2 to the 1, 2 to the second, 2 cubed, 2 to the fourth, and so on. So you always want to start from the right-hand side because that always represents your smallest place value. And as you increase to the left-hand side and you move forward to the left-hand side, your place value will increase, or I guess it will be multiplied by a factor of your base. So in this case, our base is 2. So it increases, or it increases by a factor of 2. So it doubles each time. So 2, 4, or 1, 2, 4, 8, 16, 32, and you just keep going. The other thing that we talked about is not just the place value, but the coefficients for each place value. We discussed that if you want the actual value of a number, what we can do is multiply the value for that place value by the place value itself. So in this situation right here, where we have this place value, the one's place value, which is currently being occupied with the number 2, that was the same thing as multiplying 2 times 10 to the 0 power. So the number times its place value. This next one over, 4, and then, which is in the tens place value, that was equivalent to 4 times 10 to the first power. And by expanding it, we were able to see it was easily converted back into the original number. If we were to calculate this all out, that should bring us back to this number. We did a couple of examples using this in binary, however, so we could convert it into a decimal number. So in this specific case here, we have the number 1, 0, which is a binary number, and we converted it into a decimal number by using the place values. So the 0, the most right-hand number, is 42 to the 0 place value. So we see that right here. And then the 1 is in the 2 to the first place value. So we multiply these and then take the sum of those products. And when we simplify it all out, we get this as our answer. And that means that was our decimal representation for the binary number that we had. So we converted the binary number into a decimal number. We did 2 examples. We're going to go ahead and finish this 3rd example, then move on to our next topic, which will be going vice versa. So let's go ahead and try this one out. This one is it's a longer number. So let's go ahead and try this. So we have this one right here. This would be a 2 to the 0 power. This one would be 2 to the first power, 2 to the second. You know what? Actually, I think I was going to write it bigger because this is very difficult to annotate. How many ones do I have? 1, 1, 1, 1, 1, 1, 0, 1, 0, 0. So when I go ahead and figure out what is what, this is our 2 to the 0, 2 to the first, 2 to the second, 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, 2 to the eighth, and 2 to the ninth power. Now we have to multiply the values that we have with the place value. So value times place value, and then take the sum of all of those. So this times this, plus 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 this times this. Now just keep going. Notice that 0 times anything is always going to be 0. So I'm just going to ignore this, this, and this because 0 times anything is 0. So now I'm just going to go ahead, calculate everything else that I have. So this is equal to 2 to the 9th plus 2 to the 8th plus 2 to the 7th plus 2 to the 6th plus 2 to the 5th plus 2 to the 4th plus 2 squared. Everything else, the ones that had the zeros, I am ignoring because I know that will not make any impact on the number that I have. So now I'm going to let's go ahead and do this. So 2 to the 9th is 512 plus 256 because that's 2 to the 8th plus 128 for 2 to the 7th plus 64 for 2 to the 6th plus 32 plus 16 and plus 4, whatever that sum is. Oh, is it 1012? 2 to the 9th. Oh, the entire sum. I'm not sure about the entire sum. We could calculate it though. 5, 1, 2, plus 2, 5, 6, plus 1, 2, 8, plus 6, 4, plus 32, plus 16, plus 4. It is a grand total of 1012, and that will be our decimal representation for this number. So I'm just gonna go ahead and surround that with a 10, just so that it's definitive that it is a base 10 number. Something, I'm not sure if I mentioned this last week or not, if there is no base, you can assume that it's a decimal number. So like normally if we have a number surrounded by, let's say a 3, that is a base 3 number. So meaning you can only have digits 0, 1, and 2 in that number. But if you see another number with no parentheses around it, you can assume that it's a decimal number. So but in this case here, there were no numbers, but it specifically says change the following binary numbers. So you were able to assume that these are binary numbers. But in other situations, if there's no context, just assume that it's a decimal number unless otherwise specified. Any questions so far? Okay, so we did converting binary to decimal. So now we're going to do the opposite way, decimal to binary. As you can see with binary to decimal, the thing that we just did before, it was a lot of multiplication going on. There was a lot of exponents. So when we convert the opposite way, so instead from binary to decimal, when we go to decimal to binary, we should expect some kind of inverse operation. So instead of exponents and multiplication, we should expect to see some division. And that's exactly what happens when we go from decimal to binary. So when you want to convert from decimal to binary, you want to divide, and you are most interested in the remainder. So let's say, for example, in this example, we are converting. In this example, we are converting from 61, a decimal number, to binary. So you start with 61 here. This is what you start with. And because binary is a base 2 number, we will divide by 2. 61 divided by 2 gives you a quotient of 30 with the remainder of 1. Then you go ahead and divide your new quotient by 2 again, because 2 is your base. So we divide it by 2. 30 divided by 2 gives you a quotient of 15 with the remainder of 0. Then we're going to go ahead and divide your quotient by 2 again. Yes, we're going to divide the quotient by 2. So this 15 divided by 2, and we get a quotient of 7 with the remainder of 1. We're going to go ahead and divide our quotient again by 2 because 2 is our base, and we'll get 3 with the remainder of 1. We're going to go ahead and divide it again. Divide our quotient by 2, and then we'll get the quotient is 1 with the remainder of 1. And we're going to go ahead and divide it one more time by 2 so that we get our quotient is 0 with the remainder of 1. Your solution to your conversion, so from decimal to binary, the binary number that you have just converted starts from the most recent remainder and works its way backwards. So the binary number you would have gotten is 1, 1, 1. So sorry, 1, 1, 1, 1, 0, 1. This is our binary number. 61 is 111101. So let's go ahead and just verify that this is our correct answer by converting 111101 back into a decimal number. Let's go ahead and double check. Oh, it's not showing up. 1 second. There we go. Okay, is 111101 equal to 61? So that's what we're going to go ahead and double check here by converting this number back into decimal. So we have 111101. This is our 2 to the 0 power, 2 to the first power, 2 squared, 2 cubed, 2 to the fourth, and 2 to the fifth. When we write this all out, remember, we're going to ignore that 0 because 0 times anything is 0. And we're going to take this or find the sum of the products or find the sum of the exponents. So we have 2 to the fifth power plus 2 to the fourth power plus 2 to the third power plus 2 to the second power plus 2 to the 0 power, which is equivalent to 32 plus 16 plus 8 plus 4 plus 1. In total, we should get 40. 61. Yay. So this we've double checked it that our answer is correct. So the trick to this is to continuously divide until you get 0 as a quotient. Divide the number by the base until you get 0 as the quotient. The quotient. So that is what like your algorithm is. So you're gonna just keep doing that. And then your answer, your solution, so the binary number will be the remainders from the bottom to the top. So that is how you would find your binary number given a decimal number. Let's go ahead and try a couple examples. I think examples could be very helpful. So let's start with the number 52. So 52 is a decimal number and we want to convert it into a binary number. So we start with the number 52 and we are going to divide it by the base. So the base that we're trying to convert it to, because it's a binary number, is base 2. So we will divide 52 by 2. Upon division, you should get that your quotient is 26 with a remainder of 0. We are going to divide again because our quotient is not 0 yet. So we're going to keep going until our quotient is 0. So we're going to divide it by 2. 26 divided by 2, you will get a quotient of 13. And this also has a remainder of 0. Our quotient is not 0 yet, so we will divide it by 2 once again. So 13 divided by 2, you will get a quotient of 6 with a remainder of 1. So we will divide this by 2. 6 divided by 2. Remember, we still haven't gotten 0 as our number. So I don't know why I keep pushing that. We would get a quotient of 3 with a remainder of 0. Our quotient is still not 0, so we're going to go ahead and divide this by 2, and we get quotient of 1 with a remainder of 1, which we will divide once more. And then finally, we get a quotient of 0 with a remainder of 1. Start from the bottom and work our way up. So we have our number 1, 1, 0, 1, 0, 0, and that would be our binary number. That would be our solution. Let's try this again, but with the number 111. So this 111 is a decimal number, which we are going to be converting into a binary number. So let's go ahead and do this one. So 111, and then it's a binary number still, or that's what we're trying to convert it to. So that means we're going to divide it by 2. 111 divided by 2. We would get 55 as the quotient and a remainder of 1, which we will, well, the quotient, we will divide by 2 again, because our quotient is not 0 yet. We want to keep going until we get a quotient of 0. So 55 divided by 2, we get, there is color I need. We would get 27 with a remainder of 1. This one, once again, we are going to go ahead and divide by 2. 27 divided by 2, we would get 13 with a remainder of 1. Dividing this by 2, we would get 6 with a remainder of 1. 6 is still not 0, so we're going to go ahead and divide this by 2 again. And we would get 3 with a remainder of 0, which we're going to go ahead and divide. Or the 3 we're going to divide by 2 again, because 3 is still not 0. So we get 1 with a remainder of 1. Do one more division because we're still trying to attain that quotient of 0, and we get the quotient is 0 here with a remainder of 1. Now we're going to go ahead and start from the bottom and work our way up to get our binary number using our remainders, and we get 1, 1, 0, 1, 1, 1, 1. And this would be our binary number, a binary representation of 111. There's actually a joke. They say there's 10 people, there's 10 different kinds of people. One that knows binary and one that doesn't. You guys get it? You guys get it? No? Okay, if you guys get it, that means you guys have learned in this class. If you guys don't understand it, study a little bit harder. All right, so we talked about the decimal number system and we talked about the binary number system, and I'm going to introduce 2 more to you guys, the octal and hexadecimal. So I already defined number systems with the defined number systems, the decimal number system, so the base 10, and then also the binary number system base 2. So we'll just talk about the last 2 bullet points, the octal and the hexadecimal number system. Octal is base 8. Hopefully you guys are able to decipher that just by seeing oct, like OCT, because like octopus and like octagon, 8. So we have only 8 digits that are available to us, 0, 1, 2, 3, 4, 5, 6, 7, meaning numbers 8 and 9 are not available for use. And then we have the hexadecimal system, which is base 16. So what's unique about this is that we have letters. We have alphabetical characters that will be used to represent numbers. Because hexadecimal is base 16, that means you need 16 digits. After you surpass 9, however, when it comes to the number system that we use, after 9 is 10. 10 is 2 digits. So you can't represent 10 as a single digit unless you allow a different character to take its place. So when we see A is not, A isn't just A is going to be 10. B is 11, C is 12, D is 13, E is 14, and F means 15. So you'll see these letters popping up here and there when it's in a hexadecimal system, but these represent numbers. A means 10, and then like all the way up to F, which is 15. You will hear me, instead of calling this hexadecimal, I'll just call it hex, because hexadecimal is 5 syllables and hex is 1 syllable. So you'll just hear me abbreviate it to just hex. But when I say hex, that's me saying hex, that's me actually referring to the hexadecimal or the base 16 system. When it comes to conversion with these, it might get a little bit overwhelming, but as long as you understood the things that we've talked about so far, converting to like from decimal to binary and from binary to decimal will do okay, because the strategy is pretty much identical. So let's go ahead and take a look at this. So converting octal to decimal system. It's not bad at all. It's exactly the same strategy. We want to take advantage of the place value. So this is the example that we have right here, 6523 from the octal system into the decimal system. So we start from the right-hand side and use place values. So 6523, this is octal system. So that's base 8. 8 to the 0 power, 8 to the first power, 8 to the second power, and 8 to the third power. Then we're going to go ahead and find the product of our coefficient, which is the value in a specific place value, and then multiply it to the place value. Oh, this is 8 to 3. These should all be powers. Well, actually, fine. We'll just go ahead and rewrite this all. So, right here, this place value 6, this 6, which is in the place value of 8 to the third power, this would be equal to 6 times 8 to the third power, just like what we did in our binary system, where we multiplied the place value multiplied the coefficient to the place value. This one is a little bit easier because the largest number that we could have possibly had was a 1 in the binary system, because you only have 2 numbers, 0 and 1. If you had a 0, then 0 times anything would make it cancel out. But if we have a 1 here, that just means you just have the place value itself. This one in this case is just a little bit different because we have larger values that can occupy place values. So instead of just 0s and 1s, we have up to the number 7 in the octal and up to the number 15 in hexadecimal. But regardless, the entire process is still the same. Then we have the next place value, 8 to the second power, which has the value 5 in that position. So this would be plus 5 times 8 to the second power. Then in the next place value, this one over here, we have the 8 to the first place value, which is 2 times 8 to the first power, because you can see that in the value that is occupying that place value is 2. So we multiply 2 times and its place value 8 to the first power. And last but not least, we have our rightmost place value, which is 8 to the 0 power, and its value 3. So we would multiply this and we could simplify. So 3 times 8 to the third power ultimately, I guess, should get you 3072. But we could go ahead and verify if my math above is correct. So let's just go into solving the rest of this. 3 times 8 to the third power, or sorry, not 3, 6 times 8 to the third power, this part right here. 8 to the third power is going to be 512. So 6 times 512 plus 5 times 8 squared, so plus 5 times 64, plus 2 times 8, and then plus 3 times 1. So I'm running out of space, so I'm just gonna do like a little arrow and then plus 3 times 1. And when we go ahead and calculate the rest of this, 6 times 512 is indeed equal to 3072. 5 times 64 is 320. 2 times 8 is 16. 3 times 1 is 3. And when we add that all together, we should get 3,411, which will be our decimal representation of our previously written out octal number 6523. So that was octal. And now we're going to do a hexadecimal example. So hexadecimal has exactly the same step-by-step strategy. It's just that the numbers are different. The numbers are different in two ways. First of all, it is because it's a base 16, that means our place values would be in powers of 16. So 16 to the 0, 16 to the first, 16 to the second power, and then you keep going. The other thing is the letters. Because it is base 16, we surpass 9 in our number system. So that means we have normally two-digit numbers like 10, 11, 12, 13, 14, 15 that have to be condensed into alphabetical characters so that it will be represented as one digit. So in our case here, we have A and D. A and D have different meanings. Remember, A is 10 and D is 13. So when you are converting, be careful of that. A is 10 and D is 13. I'm going to go ahead and write that for our place values so that when we are converting, it's not as complex and we're able to know what number, what character is represented by what number. I'm going to write it a little bit more to the side. That way I have a little bit more room to work with. So I guess A is normally is our 10 and our D is our 13. Our 2 is just 2. In terms of place values, starting from the right-hand side, that's 16 to the 0 power, then 16 to the first, then 16 to the second power. We are going to now go ahead and multiply. We're going to multiply our number in a certain place value, so our coefficients, with the place value itself, then find the sum of all of those values. So let's go ahead right here, 10 times 16 squared. So 10 is our value and 16 squared is our place value. Plus, then our next one is 13 times 16 to the first power. Then our last one, 2 times 16 to the 0 power, which would be 10 times 16 squared is 256, plus 13 times 16 plus 2 times 1, because 16 to the 0 power is 1. And if we find the sum of all of these, we should get that our, or actually, if we simplify this, so first I'll multiply each individual part and then find the sum of these expressions, we should get 2,770 as our decimal representation of our previously written out hexadecimal number. Any questions so far? Okay, so next we have the same, or not, I guess not really the same, but we have converting the other direction around. So we converted the numbers into decimal numbers. Now we're going to convert the decimal numbers to different number systems. We talked about earlier today how to convert from decimal to binary. Now we're going to take that application and do it with different numbers. What made this special was the fact that it was a binary number. And when we were converting to a binary number, we always divided by 2 because binary is a base 2 system. Now we're dealing with other numbers, base 8 octal or base 16 hexadecimal. The only difference is that instead of dividing by 2, we will be dividing by 8 or 16, depending on what our number system is. So let's go ahead and try these out. We have 175, and we're going to convert that into our, wait, oh, sorry, I skipped ahead. Right here, we had 1,293. We're going to convert it to octal. So let's go ahead and try it just by dividing everything by 8 consistently. So let's start with 1293. This is our original number. Divide it by, because octal is a base 8 system, we will divide this by 8. Because I don't want to make any mistakes, I'm just going to calculate it for this. We have our quotient, so 1,293 divided by 8 is 161 with a remainder of 5, I think. Yeah, so the remainder of 5. Now we're going to go ahead, because our quotient is not yet 0, we're going to go ahead and divide this by 8 again. Colors. We're going to divide this by 8, so we would get a quotient of 20 with a remainder of 1. Still not 0, so we're going to go ahead and divide this by 8 again, where we get 2 with a remainder of 4, and we still have not reached 0. So we're going to divide one more time, so we get 0 with a remainder of 2. Starting from the bottom and working our way up, that would give us our octal representation of this number, which would be 2415. And that would be our answer. And on the right of that, we're going to convert 102,382 hex. And remember, hex is short for hexadecimal, so this is base 16. What a lovely large number. Why did I choose that number? Should have chosen something smaller. Okay, but let's go ahead and just dive right into this. Same thing, the same exact process. It's just that we have this massive number, 102,380, and we are going to divide this by 16. I'm going to use a calculator because I don't know that number at the top of my head. And we get that the quotient is 6,398, and we have a remainder of 12. Still a big number, but that just means that we have to divide it again by 16. So 6,398 divided by 16, we get that the quotient is 399 with a remainder of, what is this remainder? 14. Divided again, because we're still not quite there. Divided by 16, 399 divided by 16, we get 24. With the remainder of, what is this remainder? 15. And dividing it again. So 16 right here, 24 divided by 16, we get a quotient of 1 with a remainder of 8. Divide one more time and we get 16 with a quotient of 0 and a remainder of 1. we're done because our quotient is 0. So start from here and work our way up, and we get 1, 8, and then 15. So 15 we have to convert into a letter because we have our single digits, or they need to be single digits and not double digits. Remember, 15 is going to be F. Where was that slide? 15 is F. If you guys don't remember, you could always just count. I personally don't even have these memorized. So like I always have to be like A, B, C, D. I have to like count in my head. That's perfectly fine as long as you know how to derive what letter it belongs to which number or vice versa. So this one right here is F. This one right here would be E. And then this one right here should be C. So we have F, E, C, and this is our hexadecimal number. So so we've covered 3 important number systems, or other than decimal, we have 3 important number systems: binary, octal, and hexadecimal. And the reason why that these are important is because they're all powers of 2. Binary is obviously important because you have the 2 digits 0 and 1, and computers know how to interpret zeros and 1 only. Octal and hexadecimal is a little bit easier for us to understand because there's more numbers. If you were to see like a whole bunch of zeros and ones, that has no meaning, or it has very little meaning to humans because we don't know what that number actually means, because a binary number is so much longer than an octal number or a hexadecimal number or even a decimal number. As we saw in these examples right here, the number 170 versus its binary counterpart. So we saw the number 170 right here versus what it is in binary, or the number 1012 here versus a number in binary. When we look at it, the binary number means nothing to us. It's very difficult to interpret the meaning of a binary number. So we have octal numbers and hexadecimal numbers to help us because these are powers of 2, which allow the conversions from binary into these other number systems to be a little bit easier than decimal. So let's go ahead and talk about how do we convert from binary to octal, binary to hexadecimal, or the other way around, hexadecimal to binary, or octal to binary. Let's talk about those here. So converting between octal and hex to binary, or the other way around. Hopefully you guys know that 2 to the 3rd power, 2 cubed is equal to 8. 2 to the 4th power is equal to 16. This is very important knowledge that you guys need to know in order to do this nice little trick here. If you did not know this, do the math quickly before you start following along on the next slide. The reason why this is important, 2 to the 3rd power is 8, and 2 to the 4th power is 16, is because of this. If you want to convert octal to binary, the trick is to take each individual digit. So this 3 right here, and we're going to convert it into a binary number. Let's make this a little different. We convert it into a binary number. 3 as a binary number is 1, 1, but we want it to be a 3-bit binary number because 2 to the 3rd power is equal to 8. And then we do this for every digit. So 2 is normally 1, 0, but then we want to write it as a 3-bit binary number, so 0, 1, 0. And 1 is normally written as just 1, but we want this to be a 3-bit binary number, so we just write 0, 0, 1. Then we concatenate. Hopefully you guys remember that word concatenate, which is just like sandwiching everything together sequentially. So one after another, combine it. And then we should find our binary representation for 1, 2, 3 octal. So you can see 0, 1, 1 from here. Let's use be able to see 0, 1, 1 from here. 0, 1, 0 from here. And this one right here, 0, 0, 1, we only have one here. That's because the numbers, the leading zeros are useless to us. It's like if I ask you what is 1 plus 2, and then you say 0, 0, 0, 3. You could just say 3. Technically, you're not wrong if you say 0, 0, 0, 3, but the leading zeros have no meaning. These leading zeros, however, this leading zero right here and this leading zero right here are indeed important because they are, they're not at the very, very beginning of the number. These zeros are at the beginning of the digit, but when it's used for conversion from an octal to a binary number, you need to keep that in there. You can't lose leading zeros of a digit unless it is at the very, very beginning of the binary number. When we do hexadecimal to binary, it's the same exact concept, except because this is 2 to the 4th power, we want to write it out as a 4-bit binary number as opposed to a 3-bit binary number as it was done in octal. So we have C. Remember, C is normally 12. So 12 as a 4-bit binary number is 1100. We had B, which is normally 11, written out as a binary number is 1011. And we have A written out as a binary number. A is normally 10, is 1010. So by concatenating these 3 digits together, or these 3 now binary numbers together, we have 10 or 1100. So here is 1100. Then we have 1011, so 1011, and 1010, 1010. So you just concatenate them, squish it all together. Going the opposite way, actually, should we do examples first? Actually, I don't know if we have time for examples. Let's just go through the rest of this. We'll talk about converting the other way around, binary to octal and hexadecimal. So this one right here, so this one we go in the opposite direction. So we have binary numbers and we want to convert to octal. Same concept, it's just you have 8 is 2 to the 3rd power, so we want to group 3 bits and convert to octal, starting at the right. I cannot emphasize that enough, you always need to start at the right. Do not start on the left. So we have 3 digits right here, 0, 0, 1. Then the next 3 digits over, we have 101. Here, we have only 1 and 0. So we're going to go ahead and leave a 0 as a placeholder, and we will use that. Then we're going to go ahead and convert it into decimal numbers, I suppose you can call it. So 001, this is normally equal to, this is normally 1. So that's the reason why we have the 1 as the rightmost octal digit. 101 is 5. That's the reason why we have 5 as the middle digit. And 010 is 2. So we have 2 as the leftmost digit. So the trick from binary to octal and hexadecimal is to group in groups of 3, then go ahead and convert that into like a decimal number, or you could think of it as an octal number as well. I prefer to think of it as a decimal number because you know for sure you won't exceed, like you'll be safe, you won't exceed the possible digits that an octal number can be. So you won't go past 7. So converting to octal, converting to decimal in this particular situation would be the same. Here, if we convert from binary to, binary to hexadecimal, this is 2 to the 4th power, so you will group 4 bits together, starting from the right. Always start from the right. If you start from the left, you'll get it's possible you'll get the right answer, but it's more likely that you'll get the incorrect answer, to be honest. So always start at the right. So we have 1010, that would be this group over here. And then you have 1001, which is this group right here. And finally, you have our last group, just a 1, 1, 0. So we're going to go ahead and leave a placeholder of 0 at the front, and that would give us our last number. So here we're going to go ahead and convert each number. 1010 is normally equal to 10. This is normally equal to 10. But 10 is 2 digits. We need to convert it into our single digit value that we are, or hopefully you guys will become comfortable with, which would be A. So this is A, and we will make that our very last digit. 1001, this is equal to 9. So we're going to make that our middle digit. And finally, our leading digit right here, 0110, that is 6. So that is our very first digit, our leading digit. So when given 110, 10011010, the binary number, just group and then convert straight into hexadecimal. And the only reason why this trick works is because we have powers of 2. So 2 to the third power is 8. So that means a binary to octal, you want to always use groups of 3. 2 to the fourth power is 16. So that means if you want to convert from binary to hexadecimal or hexadecimal to binary, you're going to use groups of 4. Which also means that if you try to use this trick for 2 irrelevant numbers, so binary to decimal, so base 2 and base 10, this trick would not work because 10 is not a power of 2. If you want to convert from binary to decimal, decimal to binary, you have to just use the methods that we talked about before. The methods over here where we use the place values, or here where we talked about the division. So binary to decimal, decimal to binary. Hexadecimal to decimal, decimal to hexadecimal. There's no power relationship between those two. So this is what you have to use. That's a different story from binary, hexadecimal, and octal though. So pros and cons to what we're talking about here. But there could be shortcuts. So I would say what we talked about here would be the shortcut method when you're using powers of 2 only. So once decimal is factored in, you cannot use this. Any questions? It's a lot of math. Hopefully you guys are like following along with a different sheet of paper. It's quite a lot. How many slides do we have left? Okay. I'm going to talk about one more quick thing, and then I'm going to revisit it next week, and that is the ASCII table. So hopefully you guys remember the ASCII table when we were talking about strings in Python. Strings in Python are, or every character in not just Python, but every programming language is given a numerical value. And the numerical values are normally stored as binary numbers, as you can see. So for example, our letter A, before we were looking at the decimal values, but now you should be able to see what it is, whether it's an octal, binary, hexadecimal, or decimal. So it's not just decimal now. So the character associated. The reason why this is important is because data is actually stored as binary digits, or in like hexadecimal digits, or I guess octal digits. Technically it's binary, but once again, we talked about how binary is difficult for people to understand. So what we do normally is we convert it into hexadecimal or octal, so the numbers are smaller and it allows for a little bit more interpretation. So we're able to interpret octal and hexadecimal much more easily than binary numbers. So text data is normally stored in binary numbers, which can easily be converted into hexadecimal or octal. And we can see, like, for example, S. The character S is not actually S. It's actually 83. The character P is not actually P. It's not stored as the value P. It's actually stored as the value 112. So this is something that for you guys to just think about for now. I don't think I'll have to completely talk or to finish this topic today. We'll pick this up next week, where we'll talk about converting text data using our knowledge about binary, decimal, and hexadecimal. And we'll also talk about storage. So when you guys, or most of you guys have smartphones now, how much memory does it have? Is it like 100, is it 64 gigabytes? Is it 128 gigabytes? Is it 256 gigabytes? Or what about your laptop? Is it 512 gigabytes? Is it maybe a terabyte? Those values, where do they come from? And that keyword bytes. We talked about bits and bytes and how they would not exist if we didn't have binary numbers. So we'll bring it all together and we'll finish our discussion about binary numbers next week.